Hello. So this is video number 2 of section 3.1. And so in this section, or in this video, we're going to finally calculate the determinant of not only a 2 by 2, not only a 3 by 3, but we're going to learn how you can calculate the determinant of an n by n matrix. So it turns out that the definition is very similar to how we defined it, well, actually for both a 2 by 2 and a 3 by 3. So if A is an n by n matrix, the determinant of A is just defined to be A11 times the determinant of the submatrix A11 minus A12 times the determinant of the submatrix A12. And basically how this works is we just keep going across the first row of A, multiplying by the entry of that matrix, alternating plus minus, and then multiplying by the submatrix obtained by deleting the particular entries, row and column. So we saw an example of that last video for a 3 by 3 matrix. So what I want to do here is give you an example of how to do it for a 4 by 4 matrix, and then show why this turns out to be a very inefficient way to calculate the determinant in the long run, and how we can calculate determinants more efficiently. So we've seen this definition. So by this definition, if we wanted to calculate the determinant of this 4 by 4 matrix, this is what we would get. So what would we get? Well, under this definition, what I'm supposed to do is take this 1, delete row 1, column 1, so that leaves me with this 3 by 3 matrix here. So multiply 1 times the determinant of this 3 by 3 matrix, then subtract -2 times the determinant of the 3 by 3 matrix I obtain when I delete row 1, column 2. So that's here. Next, I do 5 times the determinant of the 3 by 3 matrix, where I delete row 1 and column 3. So that's here. And finally, 2, or -2, right, because I have to go plus, minus, -2 times the determinant of the matrix where I delete row 1 and column 4. So, as we said before, the determinant can be calculated recursively. So what I would have to do then is calculate 4 determinants of 4 different 3 by 3 matrices, which, as we saw already, is kind of annoying to do. And then add everything together, work everything out, and hope that somewhere along the lines we didn't make an arithmetic error, which I know if I had to do all 4 of those, almost guaranteed the first time around I would make an arithmetic error. In fact, the example at the end of this, so sort of the goal of this lecture is to find a better way to row reduce this, and even, or not row reduce, calculate the determinant of this. And even when I was doing the better way, which takes less calculation, I made an arithmetic error. So, and I had to go back and check my work and, work everything out. So, doing it this way with all of these steps is possible. It's definitely not the most efficient way, as we'll see. So the goal of this, how to calculate determinants efficiently. To do that, I want to go back to how we calculated the determinant of a 3 by 3 matrix. And I want to look at sort of maybe a different way we could have done it. And so to do this, I want to, for a brief moment, recall our general 3 by 3 matrix. So again, here we're indexing each of the entries by its row, then column. And if you'll remember, we had the very long way of writing out the determinant of A. And I want to bring this back for a specific reason. So I do apologize for reminding everyone that this expression exists. But so as I as I write this out, sort of be thinking, so remember when we originally worked with this expression, we ended up shortening this expression by finding sort of pairs of terms that for which I could factor out a like term. And so be sort of thinking about that while I define the rest of this, because that's sort of going to be a trend, is how can we sort of factor this and rearrange this in a way to simplify it. But for now, here's the full determinant written out. So in order to do this, I want to introduce yet another definition that will give some insight as to what we were doing in the first video. So given an n by n matrix A, the ij cofactor. And so this definition is basically just going to be used to further shorten determinant notation. So we say the ij cofactor of A, which will denote C sub ij, is equal to -1 to the I plus j times the determinant of the submatrix A sub ij. So the ij cofactor of A is basically just, if you think about how we originally wrote out the determinant of a 3 by 3 matrix, right? So under the definition of determinants and under the definition of determinants of 3 by 3 matrices, this was our this was how we defined the determinant of a 3 by 3 matrix. Oop, should be a times determinant. And so notice that what defining a cofactor like this does for us is it allows us to sort of even further shorten this notation, because we can write out this original definition of the determinant like this, where here each of these are just the cofactors of the matrix. So what this is it's a way of encoding not only the determinant formed by, or calculated from the submatrix A11, A12, A13, but also encodes whether or not that determinant will pop up as a positive or negative term in our sum. And so you can actually see that if the indices in the submatrix sum to an odd number, then this will always be a negative one. If they sum to an even number, this will always be a positive one. So what we did here is called cofactor expansion along the first row. So this method of calculating the determinant, and so sort of giving away a punchline here that there are going to be multiple methods of calculating determinants. This method of calculating the determinant is called cofactor expansion along the first row. So the reason is that basically when you're working through it, right, we're always working across the first row to determine not only this term here, but the submatrix that we use in calculating each of these smaller determinants. So you can think of it as like the first row is sort of deciding what's going to happen. All right, so why did I introduce this sum? Well, I claim if we group together the correct terms. And so what I'm going to do is I'm going to use 3 different colors here to group together the terms I want to use. So if we group together that term and that term, then we do this term and this term. And then finally, we do these 2 terms. I claim we can actually write out the determinant of A in a slightly different way. So let's see what we get if we factor out the like terms for each of these pairs and how we can write out the determinant differently. So notice doing this, well, the first 2 terms, well, actually we'll do these 2 terms, right? So I get negative A sub 1, 2 times the determinant of A21, A23, A21, A23, yeah, that's right, A31, and A33. Sorry, I forgot that we were multiplying this by -1, so the order here was throwing me off. All right, so next, if we look at these 2 terms, we can factor out an A22. And notice in doing so, I'm then multiplying by the determinant of the following matrix. A11, A13, A31, and A33. And then finally, minus A32 times the determinant of A21, A11, A13, A21, A23. So this is a little weird, but notice what I've done is, again, just taken, so in the 2 green terms, the common factor was A12. In the 2 red terms, the common factor was A22. And in the 2 blue terms, the common factor was A32. And each time I could find a way of organizing this so that I was multiplying by the determinant of what it turns out is a submatrix of A corresponding to the indices of the term I pulled out. And not only that, observe that the 3 terms I pulled out are all in the second column. So basically, I just did down the second column exactly what I had done across the first row originally. And so it turns out that this is equal to A12 times the cofactor C sub 12 plus A22 plus the cofactor C sub 22 plus A32 times the cofactor C sub 32. And this you might call cofactor expansion across the second column. And so what's cool about this is that I get the same answer no matter what, right? And the reason is, for this reason, it just sort of depends on how I want to group the terms together. And we're never actually going to think about determinants like this, but the reason I can get the same answer doing cofactor expansion across the second column as I could across the first row was that it's sort of just a personal preference of how you want to group these terms together. But so it turns out that for any size matrix, this type of thing works. That is, I can calculate the determinant by doing cofactor expansion actually across any single column or any single row. And I do it much like I had done with the first row technique, where I sort of pull out that element in the first row or column, whichever one I choose, multiply by the determinant of the corresponding submatrix, or if you prefer, multiply by the corresponding cofactor. Then just work my way across the row or down the column, pull out the term, multiply by the corresponding cofactor, and so on. And so this fact, which we will state as a theorem, and then we will use to work on that same example that we started with, is what's going to make finding determinants so much easier. And so this will be your main tool. This theorem will be your biggest tool throughout the course for finding determinants. So the determinant of any n by n matrix can be calculated by cofactor expansion across any row or column. And so if this is the case, here's what it looks like across row I. So it's the first entry of row I times the corresponding cofactor plus the second entry of row I times the corresponding cofactor, all the way up to the nth entry of row I times the corresponding cofactor. And so that's what's going on in this sum. Or we can do it across any row j. And again, when I do it, I'll show that I don't really think about it sort of like this sum might have you think about it. I'll show you sort of the way I prefer to think about this. But there it is. This tells us that if we want to calculate the determinant, we can pick any row or column to expand across. And as long as we just follow that sort of method of pulling out an element, determinant of a submatrix, we will get the correct determinant in the end. So we're going to finish off by calculating the determinant now in the most efficient way possible of the 4x4 matrix A that we defined earlier. And so how do we calculate a determinant when we get to pick any row or column that we want? Well, it turns out that because of this definition, notice that each individual term in each of these sums is always multiplied by a single term from the row or column, right? So each of these a sub I 1, 2, all the way up through n terms just represent a single row that I've pulled out, or a single entry, sorry, that I've pulled out of the row or column I picked to expand across. So we want to do as little work as possible in calculating the determinant. And what number allows us to multiply a bunch of things and do as little work as possible? 0. So whenever I'm going to calculate the determinant by hand, I always want to pick a row to expand across, or a column to expand across, that has as many zeros as possible. So in this case, to calculate the determinant of A, we are going to expand across row 2. So using cofactor expansion, I can write the determinant of A. So if I'm expanding across row 2 by this definition, I'm going to multiply 0 times -1 to the, well, column 1, row 2, so -1 to the 3, times the determinant of the submatrix. 0 is in first column, second row, so I want to delete first column, second row, and so I get the following submatrix: -2, 5, 2, -4, -3, 5, 0, 3, 5. But notice, eventually I don't even have to write all of this out, because this 0 is just going to cancel all of this out. So, for now I'll do this, and so this would be plus 0 times 1 to the 2 plus 2, because here I've got second row, second column. And then I'm just going to multiply again by the determinant of the corresponding submatrix, which in this case is 1, 5, 2, 2, -3, 5, and 2, 3, 5. All right. Well, now I'm finally going to have to do work, so this will be plus 3 times -1. 3 is in row 2, column 3, so that would be -1 to the 5th, times the determinant. Well, now I'm going to delete this row, or sorry, this column and this row. This row and this column, so that'll be 1, -2, 2, 2, -4, 5, and 2, let's see, deleting that, and that, so 2, 0, 5. And then just to show the power of this last term is 0, and so notice I don't even have to, what eventually we'll see is that I didn't even have to write out any of these terms, because this 0 is just going to cancel everything else out. Oh, what the heck. For the fun of it, we'll write it out this time. So 0 times -1 to the 6th times the determinant of, well, now I want to delete this row and this column, so that should be 1, -2, 5, 2, -4, -3, 2, 0, 3. And so, like I had said, in general, like this still seems like a lengthy process, but know that, in this case I was writing out each of these terms just to sort of give an indication of how this works and how expansion works. But know that, if you were calculating this for each of these terms, you could just write 0. That would be fine. And because we know this is going to be 0. And so what I'm going to do, because we know that each of these is going to cancel out, I'm actually going to just rewrite this as -3 times this determinant. So because of cofactor expansion, it turns out that the determinant of this 4x4 matrix is just -3 times the determinant of a 3x3 matrix. And while a 3x3 is still a little annoying, it's not nearly as hard as a 4x4. And so what I'm going to do now is calculate the determinant of this 3x3 matrix. But notice, again, I can expand across any row or column I want. So this time, I'm going to expand across column 2 because there's a 0. So this is equal to -3 times, well, 2 is in the first row, second column. So that's just going to turn into a positive 2 times the determinant of 2, 5. 2, 5, 2, 5. Let's see. 2, 5. Yeah, okay. Yeah, no, that's fine. 2, 5, 2, 5. Minus 4 times the determinant of 1, 2, 2, 5. Plus, well, this last term is 0, so I just add 0. Sorry, so what confused me for a second, I think when I worked it out on my own, I expanded across the third row, and so that's why I was a little confused, but this should still work. So notice because I expanded down the second column, first I've got negative 2, but I change its sign because the sum of its indices is odd. Then I've got negative 4. Negative 4 is second row, second column, so I don't change its indices. And then the submatrix is 1, 2, 2, 5. This last term, 0, is going to cancel out whatever else happens, so we're happy there. So this would be negative 3 times 2. Now, finally, for a 2 by 2 matrix, we know how to calculate that determinant easily enough. And so the determinant of this matrix is equal to 12. So still a little tough, but maybe a little easier than had we had to expand across the first row. So big lesson, remember that when calculating the determinant, we can sort of do this process, sort of the same mirrored process that we did in video 1, but we can choose any row or column to expand across in this way. And we always want to choose the row or column that's going to make our lives the easiest, because we'll always get the same answer no matter which way we choose.